How much is an asteroid worth? I don't know how it is valued, but in reality, the value of an asteroid can perhaps be estimated by assessing its mining value. Generally, asteroids rich in metals are more valuable for mining, especially M-type asteroids considered to be the source of iron meteorites. For example, the Psyche, known as the largest M-type asteroid, whose mass is estimated to account for 0.6% of the total mass of the asteroid belt. In 2023, NASA even launched the Psyche mission, planning to reach Psyche in 2029 and begin a 2-year exploration mission. If we want to mine an asteroid rich in metals, we first need to classify the metals on it. According to mining and utilization values, these metals can be divided into 2 categories. One is rare precious metals that can be directly transported back to Earth for sale. The other is cheaper base metals, which are not cost-effective to transport back to Earth, so these metals are generally considered for in-space use on the spot. Among precious metals, the most striking are platinum group metals such as osmium, dysprosium, rhodium, ruthenium, and palladium. Their annual mining volume on Earth is very small, possibly only 20 to 30 tons, so the prices of these metals are extremely high. For example, the price of osmium and rhodium can reach thousands of yuan per gram. Previously, people thought that M-type asteroids might be pure metal blocks. If so, the content of platinum group metals in them must be very high. Calculated in this way, the value of an asteroid in terms of precious metals alone would be at least in the order of trillions. However, with deeper research, people gradually realized that things are not that simple. Currently, M-type asteroids are likely composed of a mixture of metals and silicates. Nevertheless, even so, the content of platinum group metals on asteroids is still considerable. Through research on iron meteorites, scientists have found that the concentration of platinum group metals in almost all iron meteorites is higher than that in Earth's mineral deposits. Therefore, how to mine precious metals from asteroids at low cost and transport them back to Earth will be a new direction for future space exploration. Especially when Earth's mineral deposits are becoming fewer and mining difficulties are increasing, asteroid mining will become more and more cost-effective. In addition to precious metals, base metals on asteroids such as iron, magnesium, aluminum, and silicon are still of great value as basic materials for space construction. In the future, whether building solar panels, space stations, or even alien bases, these all cannot do without basic metal materials. Although most of these metals exist in the form of oxides and need to go through a series of treatments before they can be put into use. When technology and timing are mature, compared with transporting them from the distant Earth little by little, using local materials will definitely be the best solution at that time. More importantly, the minimal volume of the asteroid belt is far greater than that of other celestial bodies in the inner solar system. Scientists calculate that in theory, the minimal reserves of just Ceres alone are more than those of Mars, Mercury, and the Moon combined. It can be foreseen that the asteroid belt will definitely become a hotly contested area in the future. However, with the current technological level, mining the asteroid belt is still unrealistic. But at present, scientists have begun to conduct on-site explorations of some near-Earth asteroids. For example, Japan's Hayabusa and Hayabusa 2 missions, the United States' OSIRIS-REx mission to sample the asteroid Bennu, and China also plans to launch the Tianwen-2 mission in 2025, targeting the sample return mission for the near-Earth asteroid 2016 HO3. These space missions, in addition to their scientific research purposes, also serve as preliminary verifications of asteroid resource exploration and related technologies, especially in spacecraft control. Unlike large planets, asteroids have weak gravity due to their small mass, which requires spacecraft to have high-precision navigation and orbit control technologies. Coupled with a series of complex sampling operations, these pose significant challenges to current aerospace engineering. However, unlike basic science, these challenges belong more to technical problems. With the breakthrough of human engineering technology, it is not difficult to imagine that in the near future, Ceres, Vesta, and those M-type asteroids rich in high-value resources will inevitably become the space targets for competition among countries. Scientists have even discovered organic matter on Ceres, and they likely originate from the interior of Ceres. In 2007, to explore the two largest celestial bodies in the asteroid belt, Ceres and Vesta, NASA specially launched the Dawn mission. Ceres, as a celestial body with a diameter of nearly 1,000 kilometers, has many characteristics of large planets compared to asteroids, so it is sometimes classified as a dwarf planet. As mentioned before, the surface of Ceres is rich in water ice, and it is considered the celestial body with the second highest water content in the inner solar system after Earth. Other celestial bodies like Mercury, Venus, and Mars are all extremely dry. The presence of water provides an opportunity for the existence of organic matter. In 2017, the Dawn spacecraft detected signs of organic matter near a crater in the northern hemisphere of Ceres, a discovery that immediately sparked scientific discussion about its origin. Scientists have always been interested in organic molecules because they are essential components of life on Earth. Although organic molecules have been found beyond Earth, most of them originate from the outer solar system, i.e., regions beyond the asteroid belt. Organic molecules on inner solar system bodies are generally thought to be brought by comets from the outer solar system, including organic molecules on Earth, with some theories suggesting they first arrived via comet impacts, a hypothesis known as the extraterrestrial hypothesis. Where there is an extraterrestrial origin, a terrestrial origin naturally exists, and the possibility of self-formation within celestial bodies cannot be fully ruled out. For example, organic molecules have been found in recent years on asteroids Ryugu and Bennu, as well as on Ceres discussed here. When the Dawn spacecraft flew past Ceres, its visible and infrared mapping spectrometer clearly detected absorption features of organic molecules at the edge of a crater. These features include a series of characteristics of long-chain aliphatic organic matter. Aliphatic organic matter refers to a class of hydrocarbons, simply composed primarily of carbon and hydrogen. According to traditional views, these organic substances should have been previously brought by comet impacts, i.e., extraterrestrial in origin. However, this view seems inconsistent with Ceres, as this extraterrestrial method could only deliver limited organic matter, making it difficult to achieve such a large coverage. Moreover, around the area covered by organic matter, besides this crater, no other traces of large impacts have been found. The crater itself is very ancient, and over millions of years, these organic substances should have been heavily degraded and diluted, rather than showing such high concentrations. Therefore, many suspect whether the organic matter on Ceres could originate from within the planet itself. In September 2024, a paper published in Science Advances specifically studied the origin and persistence of organic matter on Ceres. First, they simulated Ceres' radiation environment in the laboratory, attempting to replicate the effects of solar and cosmic radiation on surface organic matter. The results showed that these organic substances do degrade very rapidly, meaning they are unlikely to have been brought from outside and are more likely produced by Ceres itself. The organic matter we observe may be just a small exposed portion, with a large amount potentially hidden beneath Ceres' shallow surface. It is estimated that the initial abundance of aliphatic materials on Ceres may be 2 to 30 times the currently observed levels. Based on simulation results, researchers speculate that a massive organic reservoir may exist in the subsurface straight 3 to 6 kilometers below the crater's surface. Due to small meteorite impacts, landslides, and other factors, some of these subsurface organic materials are brought to the surface. Although the specific exposure mechanisms and ultimate origins remain unclear, this speculation has some supporting evidence. In 2022, scientists detected similar characteristic substances in samples returned from asteroid Ryugu by Japan's Hayabusa 2 mission. Such small asteroids have a very low probability of being impacted by comets and are generally considered to have relatively pristine environments, even preserving information from the early solar system. Recently, a paper published in the Journal of Planetary Science further supports the endogenous hypothesis for Ceres organic matter. The research team not only used spectral mixture analysis, but also employed Dawn's high-resolution spatial images to scan the rest of Ceres' surface, identifying 11 new regions with organic matter characteristics. These newly discovered areas are mostly near the equator. Compared to the organic matter found in previous craters, the organic matter here is more easily degraded by solar radiation, with relatively weak spectral signals and thus harder to detect. Finally, the significance of discovering organic matter on Ceres does not lie in whether there is extraterrestrial life, but rather in demonstrating that Ceres has internal energy sources supporting biological processes. This implies that in the future era of space colonization, Ceres could potentially serve as a transfer station and resource base for deeper space missions.